Okay then, girls. Good morning. I can see very few of you here. Can I just say that everyone who is not attending and who has not submitted a valid reason will be put absent, yeah? So we are clear on this. You either submit a medical reason why you're not here, or you are absent from the class. There is no other alternative, okay? Any questions at all? Anything you want to ask before we start this class? No questions? Nothing? Okay. So today then we'll take a look at chapter 11. I think we're almost done with this course. There are two chapters left, chapter 11 and chapter 14. Both are very easy compared to the others, so hopefully we will be fine with this. Okay, so obviously next week you will have your test 3. Please practice. There is a practice test there for you to do. Try and do it. If you have any question, please get in touch. Okay, so I repeat, all of you watching online, unless you submit a valid reason, you are actually absent from this class. Okay, so you need to submit a valid reason why you are not attending the face-to-face class. Okay, so chapter 11, we'll take a look at vector-valued functions, which are functions which basically can be written in 3 dimensions. They are in this form. R of t is ft multiplied by the vector I, g of t times j, plus h of t times k. So it's basically a vector. This is a vector, f of t, g of t, h of t. Okay? So that is the function r of t. It's a function, but its values are actually vectors. In 3 dimensions, it's like this. In 2 dimensions, in R2, the vector will only have 2 components, f of t and g of t, like this. So in 2 dimensions, it's a vector with 2 components. In 3 dimensions, it's a vector of 3 with 3 components. What is the variable here? What is the variable? T. Yeah, t is the variable. So the function r will take the variable and will give us a vector either in 2 dimensions or 3 dimensions. Okay, so first question we have here is sketch the graph of the curve traced out by the endpoint of the 2-dimensional valued function, which is given by this. So I want to graph the endpoints of this function. So let me show you how we do this. So r of t, so basically it's, what is the first component of this function? T plus 1, yeah, t plus 1 is the f, yeah, and what is the second component? T squared minus 2, yeah, like this. So think about this, the x component of this vector, what is the x component? T plus 1, okay, good. The y component is t squared minus 2. So basically what I do is I look at these 2 parametric equations, x equal t plus 1, y equal t squared minus 2, and I want to graph this function. The way we can do that is I'm going to get t from the first equation. What is t? X minus 1, yeah? And I will substitute that in the second equation. So I will get y equal x minus 1 squared minus 2. Now, this, I know what graph this is. What is this graph? Y equal x minus 2 squared. It's a parabola. Exactly. This is a parabola. What is the vertex of this parabola? 1 minus 2. Very good. Okay, great. So this is a parabola where the vertex is the point 1 minus 2. And so we can, and it opens up, yes, because, yeah, opens up because the A is positive, yeah. And it is graphed here. You can see its graph is the red thing here, where the vertex is the point 1 minus 2, like this. And you have the graph of the function. So basically, this function, by the way, for example, let me find some vectors. Yeah, some vectors. For example, what is r of 0? It will be the vector 1 minus 2. Very good. Yeah, 1 minus 2, which is the blue vector here. Can you see it? Sorry, shall I move this thing? Or are you okay with it? Okay. So r of 0 is the blue vector. Yeah. R of, let's say, they are doing 2. So let's do 2 also. So r of 2 will be the vector 3 and 1. Yeah. Sorry. 3 squared is 9 minus 2. So what is it? 2, yes? Oh, 2. 2 squared minus 2, which is 2. And that is the vector you see here. 3 along the x-axis and 2 along the y-axis. So you get the vector over there. I think they also did r of minus 2. If we substitute, it will be the vector minus 1 and 2. You can see it here, etc. So every t will give us a vector. Yeah. Well, how about r of 1? What will be the vector r of 1? If we wanted r of 1, 2 minus 1, yeah, etc. So the endpoints is the point 1 minus 2. Here the endpoint will be the point at the end of the vector, basically. The point at the end of the vector, these are what we call the endpoints. Yeah. So 1 minus 2, 3, 2. This one will be minus 1, 2. This one is the point 2 minus 1, etc. And when you put all of these points together, these endpoints together, will give you the parabola that we have here. Okay. Are we okay with this? Yeah. So that is the first question. Sketch a graph of the curve traced out by the endpoints of the two-dimensional valued function. So you look at x, y, you find an equation between x and y. Here we can see it's a parabola with the vertex 1 minus 2, and it opens up so you can graph it. The graph is given here. Yeah, this is the graph, and the equation is given. Okay, so let's have a look now. Same idea. This time we have a function, this time a vector valued function, which is given by this vector. This time, what is x? 4 cosine t, and y is -3 sine t. Yeah. So these are the x and y. Now, to graph this, the endpoints, we need to find the connection between x and y, like an equation between x and y. Okay, to do that, I'm going to do this. X over 4 will be cosine t, huh? And here, y over 3 is minus sine t. Now, if we square, now I'm going to square this, and I will add y over 3 squared. So that will give us cosine squared t plus minus 3 sine t. Let me write it like this, squared, which is 1, basically, because this will become sine squared t, so we are getting 1. So that means we're getting the following equation. X over 16 plus y over 9 equal to 1. And this is the equation of an ellipse, yes. Why did I square it? It's because I want the relation between x and y. And the only way I can find the relation between this and this is to square, really, to square this and to square this. Because I know that cosine squared plus sine squared is always equal to 1. So I'm trying to use that rule here. Are we okay with this? Yeah. So now, what shape is this? This is an ellipse. Yes, you can see this is an ellipse. We know these kind of equations. They are an ellipse, and they go, if you put y equals 0, you will get x equal 4 and minus 4. Yeah? If you put in this equation y equal to 0, so you will get x squared over 16 equal to 1, which means x squared is 16, so x is plus or minus 4. That means this ellipse cuts the x-axis at 4 and minus 4. Now, if you want to find the points where it cuts the y-axis, what do? Yeah, x equals 0, and you do the same thing. You will see that y will be plus or minus 3, and these are the intersection points with the y-axis. So therefore, yeah, this is the ellipse. That means the vectors will be always like this. Yeah. For example, if I want r of 0, yeah, what vector is r of 0? It will be 4 zeros, huh? 4, 0, 4, 0, which is this vector here. This is the vector 4, 0, yeah, etc. So different values of t will give you different vectors, and each vector will give you an endpoint. And when you put all these endpoints together, you get the ellipse we are talking about. Okay, here it's in 3 dimensions this time. Plot the curve traced out by the vector valued function. This one. Okay, the way we do that is to think this time we have x, y, z. Now, what is x? Sine t, yeah? Sine t. Y is 3, yeah, minus 3 cosine t. And z is 2t, yeah, like this. Yes. Now, if we want to find the shape of this, I can consider x and y separately, like this. Now, if I just keep x as sine t, and then I have y over 3, which will be minus cosine t, and square both sides. Yeah, square both of them. So x squared plus y over 3 squared is going to be 1, just like we did before. So we're getting x squared plus y squared over 9 equal to 1. Now, what shape is this? Think of this like 1, yeah? It's a bit like 1. What is this shape? Again, it's an ellipse, yes? It's an ellipse. Yeah, it's an ellipse in the xy plane, yes? Now, yeah, it's an ellipse. And then, because z is 2t, so it's going to kind of, this ellipse will be moving along the z-axis. So you are going to have this kind of shape.
It will be moving by 2 intervals?
Yeah, because when t is 0, for example, different, yeah, t equals 0 will give you the vector, what exactly, if you put t equals 0, x will be 0, yeah, minus 3, 0. So this vector is actually on the x, yeah, z is 0, y is also, x is also 0, y is minus 3, so it's this vector going like this. So this is actually r of, yeah, r of 0. Now, if, for example, I take t equal 1, and I want to find what is r of 1, yeah, r is a vector, or let me take pi, for example. Let's say r of pi, yeah, when t is pi, what vector are we going to get? Sine pi, which is 0, and then minus 3 cosine pi, 3, yeah, and z is 6 pi. So it's a vector, yeah, which is, x is, sorry, huh? Sorry, why am I putting 6 pi? Yes, thank you. It's just 2 pi, yes. Okay. So it was 0, what was it? 3, huh?
Yes.
And then 2 pi. Yeah. So, yeah, so it's going to be vector up like this. Yeah. R of pi. This is R of 0. Like this. Yeah. That means basically 0 on the x-axis. Oh, y, sorry, so y is 3, huh? Yeah, I think it's the wrong direction. Y is 3 and z is 0. Sorry, x is 0, y 3. So it's going to be going in this direction like this. R of pi. Okay, yeah, so it's 6 pi, 2 pi here, and then 3 on the y-axis like this. So the vector r of pi is going that way, etc. So different values of t will give you different vectors, and when you graph them, you will get all this shape. It's like a cylinder, but its base is not a circle. What is the base of the cylinder? It's an ellipse, yes. Yeah, like that. Okay. Another example here, which is a bit easier. This time we have the vector r given by this. So x is 3 plus 2t, y 5 minus 3t, and z is 2 minus 4t. Now, if you look at these equations, you should remember what this is. What is this? They are parametric equation of what? Not a plane. A line, yes, a line. This is a line. Yeah? This is a line. In which direction? What is the direction vector of this line? Do you remember? In which direction is this line? 2 minus 3 minus 4. Yeah? This is the direction of the line. It's in the direction of this vector A. And it goes through the point. Which point? 3, 5, 2. Yeah. So this vector will give you the direction of the line. And these numbers 3, 5, 2 are a point on the line. So in the end, you will get your line, which is like this. Can you see that? So it goes through the point 3, x is 3. Okay, everyone makes me. This should be 3, so? Like, oh, anyway, okay, let me remove that. It's okay. 3, 5, 2. Yeah, the point and the direction of the vector is 2 minus 3 minus 4. So you get this line here. Are we okay with this? Yeah. So graphing is not so easy here, but at least you should know that it is a line. Yeah. The direction of this line is the vector 2 minus 3 minus 4, and the line goes through the point x equal 3, y equal 5, z equal 2, and then you are okay.
How did you know that they are lines?
Sorry?
They are lines. How did you know?
How do we know it's a line?
All parametric equations are lines.
Remember, parametric equation are not always lines. These are parametric equations, for example. These are parametric equations. What is the parameter here? T, yeah? Is it a line? No, it's not a line, yeah? These are parametric equations. X equal 4 cosine t, y equal minus 3 sine t. They are parametric equations, but they don't describe a line. They describe an ellipse, etc. So, but these equations, we studied them in a long way. And what chapter? Do you remember what chapter we studied this? 12. Yeah, chapter 12 was about, or maybe 11 perhaps. No, 11 is this one. Yeah, 12. Lines in general, let me remind you. In general, if you have equations like this, x equal, yeah, x1 plus, what was it? Yeah, at, y equal y1 plus bt, and z equal z1 plus ct, then these equations describe a line which goes through the point x1, y1, z1 in the direction of the vector ABC. Yeah. So this is an important result. We did it before. Yeah. So this is a line always. Okay. Yeah. Equation of a plane is a bit different. We looked at that also. So we did this before. Yeah. Okay. Now, so that is basically a bit of a graphing and having an idea about what these parametric equations describe. Here we have a formula which gives us the length, the arc length. So let me just explain what this is. Suppose you have a function y equal f of x, yeah, that you graph in 2 dimensions like this, x, y. Let's say its graph is something like this, y equal f of x. And you want to know the length, the length of this curve from x equal a to x equal b. You want to know how long is this curve, how many centimeters in this curve. Yeah. Okay. Well, you can get it by using this formula here. This is the arc length. Yeah. Of for example, let me give you a simple example here. Yeah. Suppose you have the function f of x equal 3x plus 5, which is, what is the graph of this function, by the way? It's a line, yeah? It's a line which goes through, it's a line like this, goes through 5, yeah? And suppose you want to know basically you want to know the length of this line from x equal minus 1 to x equal 3. So you want to know the length of this. How long is this? Length of the line from x equal to minus 1 to x equal 3. How long is this? How many centimeters? Well, the formula says that the length will be the integral from minus 1 to 3 of the square root of 1 plus f dash. Yeah? Can you see the formula said? Let me go back a little bit. The formula says f dash squared dx. Can you see that? Here, What is the derivative of this function? 3. Yes. So you need to put 3 squared dx. Like this. Do you understand this? So it's the integral from -1 to 3 of square root of 10 dx. Okay, square root of 10 you can take it out. Then you integrate dx. What do you get? X from -1 to 3. So in the end, this will give you 4 square root of 10 as the centimeters or whatever the units we are using are. Do you understand it? So this is a formula that will allow you to work out the length of a curve from x equal a to x equal b. Are we okay with this? Yeah? Yeah, okay. Now, let me come back a little bit. So that's an example for the first rule here. Simple example where we use this formula to find the arc length from x equal a to x equal b. Now, the second rule, so 1, 2, is if you are given a curve in parametric form, like this. So this time, same idea, you have a curve, but given not as y equal f of x, but in parametric form. Yeah, same idea. I have a curve, and you want to find the length of the curve from t equal a to t equal b, and you want to find the length, then you need to use this formula this time. Okay? And finally, in 3 dimensions, it's a very similar, except that this time we have 3 functions. Yeah. So number 3, we have R this time, F, G, and T. And you need to find the length of the curve from t equal a to t equal b. Then you need to use this formula. So here is an example now. And let's see how we can do this. Okay. Find the arc length of the curve traced by the endpoints of the vector valued function when t goes from 1 to e. Okay. So the length, so this is some curve like this, yeah? T equal to 1 is somewhere at the beginning, and then we have t equal e here. So we want to find how long is this curve. Okay, let's do it. The length will be the square root of, what is f here? 2t, yes? So what is the derivative of 2t? 2. So to square. Are we okay with this? Plus 1 over t squared. Good. Plus 2t squared. That's it. 2t squared. Sorry, 2t. The square is outside. Yeah. And it's going to be the integral from 1 to e dt, like this. So that is going to give us the length of this curve. Without calculus, by the way, there is no way we can calculate this length. There is no, it's not like something you can measure or something. So you really need to use this formula. So let's try and calculate this. Sometimes not easy to calculate this integral, but in this case, we can do it. There is no big issues. The first thing we need to do is to simplify the inside. So it's going to give us 4 plus 1 over t squared plus 4t squared dt. Yeah, like this. Now, of course, your calculator may be able to calculate this. Okay, but let's do it by hand. Yeah. So 1 to e. What I'm going to do is I will put this into all the same denominator. So if I use t squared as the denominator, so this 4 will become 4t squared. This one will stay as 1, and the 4t squared will become 4t to the power of 4, like this. Now, integral from 1 to e, square root of, actually what you see in the numerator is 2t squared plus 1 squared. Can you see that? If you, let me, yeah. If you expand this squared will give you this term. This times 2 will give you 4t squared. And 1 squared will give you the 1. So this is exactly the same as this. And then over t squared dt. Now, I can remove the square with the square root. So this is the integral from 1 to e of 2t squared plus 1 over t, like this, dt. Can you see that? Yeah? Okay. Now, what do you think after this? How are we going to integrate this? Yes, we need to separate this, separate into two fractions. So you will get 2t squared over t plus 1 over t dt. Now, it's very easy to complete this. So it's going to be the integral from 1 to e of 2t plus 1 over t dt. And now it's okay because the integral of 2t is t squared, and the integral of 1 over t is no. Lengthy, yes, lengthy, girls, please remember. The integral of 1 over t is ln t. Yeah. Okay. After that, we substitute, so we will get e squared plus 1 with e, because ln e is 1, yeah? And then minus 1, because ln 1 is 0, yeah? So basically, the whole thing is equal to e squared. So the length of this curve is equal to e squared, which will give you maybe around 7 or 8, maybe 8 point something. Yeah? 7.98. Yeah, 7.98, which is almost 8 centimeters or whatever the units are. And that's it, basically. That is what is in this section. Are we okay with this? Or, yeah? So the main thing, of course, in your tests, etc., we will not give you graphing or so. Main important thing in this small section are these formulas, these 3 rules that will allow you to work out the length of the curve if it is given in the form of y equal fx. Then you use this in 2 dimensions. Yeah, you use this in 3 dimensions. You need to use this rule here. So that's basically. So let's maybe just do a couple of these. Okay. Right. First, sketch the curve traced out by the given vector valued functions. So we can do maybe 1 or 2 of these. So what do we do here? So we say x is t minus 1 and y is t squared. I think this one is very similar to what we did before. So t will be x plus 1 and we substitute it here. So you will get y equal x plus 1 squared, which is a parabola. This is a parabola. Where is the vertex of this parabola? Vertex at minus 1, 0. So you say minus 1, 0 is this point. Yeah? And the parabola will be like this. So that's it. And this point, by the way, what do you think this intersection with the y-axis? 1, yes. How did you get 1? Huh? You don't know?
Substitute. I think x equals 0.
X equals 0, yes. If you put x equals 0 here, you can see that you will get 1 squared, which is 1. So, yes, it's going to be. And this point, of course, is minus. That's it. So that's the graph of that. The second one, I will do this one also. Just this one, x is 2 cosine t, and y is sine t minus 1. So the way we do this is always to get cosine from one equation. Yeah, cosine will be x over 2, and the sine here will be y plus 1. So, yeah, so that means from here you can see that x over 2 squared plus y plus 1 squared is going to be equal to 1. That means the equation becomes x squared over 4 plus y plus 1 squared, like over 1, equal to 1. Now this is an ellipse but the center of this ellipse is not 0, 0. 0, minus 1, yes. So this ellipse will be centered at 0, minus 1. Yes. So ellipse centered at the point 0, minus 1. So basically, what you will get is the center is here, 0, minus 1. And this ellipse will have a length of 1 along the y-axis. And what is its length along the x-axis? 2, yeah. 2 on that side, 2 on that side. So it's going to be something like this. Yeah. So this will be 2, this will be minus 2, this will be 1, 0, yeah, minus 1 and minus 2. Like. So this is the ellipse that you will get. Yep. Okay, so 5 is going to be similar. I think it's a cylinder. This is going to be a cylinder because you can see x and y. X squared plus y squared is 4, and z is 3. So it's basically, no, it's a circle right at z equal to 3. Yeah. Okay, so I'll leave you these. You can have a look. I just want to do one more example of all of this. You can check them. I want to do the arc length of one of these. Check. Okay. 31 is very similar to the example we did. So I will leave you to do 31. I'm going to do 29. Yeah. 31 exactly like the example, so you can try it. So let's do 29. So I want to compute the arc length of this curve when t goes from 0 to 2 pi. So the length will be the integral from 0 to 2 pi, the square root of, okay, yeah, so x, I need to, x is what? T cosine t. Let me just check, by the way. Yeah, I need to, yeah, do this by the product rule. Yes. I'm just trying to see. Yeah, it's okay. We can do it. It's going to be a bit long, but it can be done. So the derivative here, we need to use the product rule. It's u dash. What is u dash? Yeah, this is like u v. Yeah, u dash will be 1. So u dash v will give us cosine t, and then plus u v dash. What is v dash? Minus. So it's going to be minus t sine t. Very good. Squared. Yes. Plus. Yeah. Again, the product rule will give us here sine t plus t cosine t. So squared. And finally, the derivative here, we need to bring 3 over 2 down, multiplied by 1 over 3. So it's going to give us half, and 2t to the power of, yeah, 3 over 2. Yeah, 1 over 2 minus 1, so it's going to be 1 over 2. Yes. And then I shouldn't forget the derivative of 2t, which is 2. Yes. Like this. So, of course, this half with the 2 will give you 1, so we can cancel that. And then I will open this bracket. So what we will do is we will open the brackets. So it's going to give us cosine squared t minus 2t cosine sine plus t squared sine squared t. So, you okay with this? Yeah. And then we open the second bracket, which is sine squared plus t squared cosine squared plus 2t sine t cosine t, and finally plus 2t, yeah, yes. Oh, I forgot to square these curves. So, this is the derivative, but it needs to be squared. So when we square, the 2 with a half will go. So it's going to be 2t, yes. dt. Is that okay? Yeah. All right. After that, we have a lot of things we can simplify. I think this and this will go. Yes? One is minus, the other one is plus. They are the same. 2t cosine sine, 2t cosine sine. Also, this and this will give us 1. So it's going to be the integral from 0 to 2 pi square root of 1. So this and this will give us 1. So we put it there. Also, this and this will give us t squared. So it's t squared factor cosine squared plus sine squared, which is 1. So that's okay. And then plus 2t dt. So it was a bit scary there, but actually it simplifies into this simple expression. Now, can you notice something about what is inside? What is it? 1 plus t squared. Can you see that? Because it's 1 squared. No, it's okay. Just if you open this, what do you get? 1 squared, which is here. 1 times t times 2, which is 2t, which is here. And then t squared, which is here. Do you understand it? Yeah. A bit like if I say x squared plus 4x plus 4, I think you should tell me that this is x plus 2 squared. Yeah, you can see that. Because x squared is this times 2 is this, 2 squared is this. So you should recognize these things sometimes. It's useful. Okay, so let me get back here. Now, the square with the square root will go. So it's going to be the integral from 0 to 2 pi of 1 plus t dt, and it's very simple now. So it's t plus from 0 to 2 pi, and we just substitute, and we get the answer as 2 pi plus 2 pi squared as the final answer of this integral. Is that okay? Or
Yes.
yeah, that's it. So that's this section done. I repeat, this very similar to the example we did, so you can try it. You can see the function len there, t squared 40. You can do it. It's very simple, very similar to what we did before. Any questions here? Anything you want to ask? Are we okay?
Yes.
Yeah. So that example 31 is very similar to this one. You can try it, and it's going to be fine. Okay, so just I'll take 2-3 minutes.